Alright, in this video we're going to take a look at the calculations that are involved in the first unit of grade 12 chemistry, calculations involving light and the Bohr model of the atom. We remember that light is often just thought of as visible light, but really that's part of a much larger electromagnetic spectrum that includes everything from radio waves to gamma radiation. Arranged like this in order of decreasing wavelengths: radio waves, then microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma radiation. You need to know those 7 regions of the spectrum. Visible light, we know, falls into a rainbow of colors that our eyes can detect. We know near the infrared region of the spectrum is where you'll find the red light within the visible spectrum, and near the ultraviolet region is where you'll find violet light. And in between those we have orange, yellow, green, blue, whatever indigo looks like, and violet. So there's the EM spectrum with the visible spectrum within it. Wavelengths are the distances between 2 consecutive crests within a wave, or if you prefer, the distance between 2 consecutive troughs within a wave. Those are the definitions. That's a definition of wavelength. Because it's a distance, it's measured in meters as the SI unit, although you will see other commonly used units like kilometers, inches, feet, micrometers, nanometers, things like that. So you will need to do some unit conversions when you're using wavelengths. Frequencies are a little bit harder to define. If you were standing watching the wave go by you, and you counted how many crests or how many troughs passed you in a given period of time, then you've measured frequency. Frequency is the number of crests that pass a given point in 1 second. Okay, so there's frequency. You don't have to count crests, you can count troughs or really any corresponding points on the waves. So the units for frequency are often simply per seconds, s to the minus 1, or hertz, Hz. And those are actually the same unit with different names. There's no conversion in between them. When you look at some of the numbers in here, I'm not sure if you can see them in the video because they're rather small. Radio waves have the longest wavelengths, and it can be in the hundreds or thousands of meters in wavelengths. Gamma radiation has the shortest wavelengths by far, 10 to the minus 12, 10 to the minus 14 meters. Frequencies, though, are the opposite range. So frequencies for radio waves are the lowest, and frequencies for the gamma radiation are the highest. So when arranged in order of decreasing wavelengths like this, you're going to get increasing frequencies like this. So wavelength and frequency must be inversely related, and that fact is revealed by this simple equation: C equals lambda nu. C is the speed of the radiation, speed of light. We're going to call speed of light for any form of this electromagnetic radiation. And as long as the radiation is traveling within a certain medium, then that speed of light is constant. So the speed of light, for example, in outer space, in a vacuum, is 3.00 times 10 to the 8 meters per second. So that's a very, very high speed. We're always going to be using that value for radiation, for the speed of light. The second letter in this equation is the Greek letter lambda, 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 and it's used to represent the wavelength. And as we said earlier, its SI unit will be the meter. Nu, Nu, is the Greek letter that we're going to use to represent frequency. So be sure you know the names and the symbols for those letters, lambda and nu. Wavelength and frequency, and as we just saw, hertz or per second are the units. Now, the debate we talked about in class was whether or not light should be thought of as a wave, that's how we've described it so far, or described as a particle. And in fact, it turns out that it has properties of both, and it's neither a wave nor a particle. So we now think of it as a particle wave or a wave particle, okay, which is not a satisfactory description. Having said that, if we think of it as particles, Max Planck gave us an equation for finding the energy on one particle of light. And his equation says E equals h nu, which means, in a rather bizarre way, that the energy on each particle of light is directly proportional to the frequency of that light. So the energy per particle is proportional to the wavelength of the light. If you think about that for a minute, your brain will hurt. H in this equation is called Planck's constant. Planck's constant. And its value is very, very small, 6.626 times 10 to the minus 34 joules, the unit for energy, seconds, joule seconds. Now, if you take the first equation and rearrange it to solve for nu, you'd get nu is equal to c divided by lambda. So if we take that rearranged equation, c divided by lambda, and put it in here where we have nu for the energy equation, we'd get another form of Planck's equation, E equals h times c divided by lambda. And those are the same equations with a little bit of algebraic manipulation. All right, now when calculating energy, you're going to get the units joules per quantum. Remember that a quantum is the unit, is the individual particle of electromagnetic radiation. You could also say joules per photon if you were talking about visible light. Sometimes we'll just say joules, but technically it's joules per quantum or joules per photon. All right, the first example of a calculation, see if you can pause the video if you know what you're doing and try this yourself. And again, show your work. Be sure you're paying attention to things like significant digits and showing equations and algebraic manipulations. So calculate the wavelength in micrometers or micrometers and the energy in joules for radio waves with a frequency of 950 kilohertz. That kilohertz jumps out at me. All right, so the wavelength and the energy, and you've given me the frequency. So I'm going to take the first equation, C equals lambda nu, and if I want to know the wavelength, I can rearrange this to say wavelength equals C divided by nu, C divided by the frequency, equals 3.00 times 10 to the 8 meters per second, that's the speed of light, divided by the frequency. Now the frequency here was 950 kilohertz. Remember, we have to use SI units on our equations. Kilohertz is not an SI unit for frequency. Hertz would be fine, but not kilohertz. So I'm going to rely on the fact that kilo means 1,000, or 10 to the power of 3, and I'm going to write that as 950 times 10 to the power of 3, and I like to see my units working out properly if I can, so I'm not going to use hertz, I'm going to use the per second instead. So 950 kilohertz means 950 times 10 to the 3 per second. Now that I've switched from kilohertz to this, notice that the per seconds will cancel, and I can see I've set this up properly. I'm going to get an answer in meters for my wavelength. So now let's calculate this answer. So grabbing a calculator, be sure you're using the scientific notation button on your calculator. So 3 times 10 to the power of 8. I didn't press the times button when I did that, right? I used the EE button on my calculator, divided by 950, and again the scientific notation, times 10 to the 3 equals 315.78. 316, I'll keep 3 significant digits because there were 3 digits in the speed of light and 3 digits in that frequency. Technically, the frequency is a little unclear whether it's 2 sig figs or 3. I'll assume it meant 3. So 316 meters. Now the question said how many micrometers would that be? So let's just do a simple unit multiplier conversion. 316 meters. I'll get rid of meter, then I'll switch to micrometer. The conversion, if you don't know it, is in your data booklet on page 2 or 3 at the bottom. 1 micrometer is 1 times 10 to the minus 6 meters. Very, very small unit. So if I take my 316 and divide by 1 times 10 to the minus 6, I get this big, big answer, which I'll switch to scientific notation, 3.16 times 10 to the 8 micrometers, or micrometers. Alright, so there's the wavelength calculated in meters and micrometers. Now we also wanted to know the energy of these radio waves. Well, to do that, I'm going to use Planck's equation from above, and I'll use the E equals h nu form since we were given the frequency. So E equals h nu equals 6.626 times 10 to the minus 34 joule seconds. And notice if I take my same conversion earlier, 950 kilohertz becomes 950 times 10 to the 3 per second. Now notice s to the positive 1 times s to the minus 1 is s to the 0, which cancels out. And so I'm going to be left with joules, which is the unit for energy. As we talked about earlier, technically joules per quantum will be the unit, since we're finding out the energy on 1 quantum of this radiation. So one more time with the calculator and using the scientific notation button, 6.626 times 10 to the times 10 to the minus 34, Planck's constant, times 950 times 10 to the 3, the frequency, 6.29 times 10 to the minus 28 joules per quantum. 3 significant digits again in the energy. Alright, let's try a second problem involving those same equations. Visible light, we said earlier, falls from 400 to 700 nanometers. What's the range of frequencies within that visible spectrum? Those are the range of wavelengths. What's the range of frequencies? Pause the video and see if you can do that yourself. So we're going to take our equation C equals lambda nu, and we're just going to solve for frequency. So frequency equals C divided by lambda. So using the first wavelength, we'll get 3.00 times 10 to the 8 meters per second divided by 400 nanometers. So nanometers we're going to have to deal with in our data booklet on, I wish I had my booklet with me, it's page 2 or 3 at the bottom. The prefixes are shown there, and nano means 10 to the minus 9 meters. So now, dividing with my scientific notation button, 3 times 10 to the 8 divided by 400 times 10 to the minus 9, we get 7.5 times 10 to the 14. And the units here are going to be per seconds, or if you prefer, hertz. Okay, now the question did not tell us a particular unit for frequency, so I'm going to leave it like that. So that's the one end of the spectrum. In fact, since that was the 400 nanometers, that's the shorter wavelengths, that's the violet end of the spectrum. Now I'll do the same thing with the red end of the spectrum. The nu equals C divided by lambda, 3.00 times 10 to the 8 meters per second, divided by 700 times 10 to the minus 9 meters, 700 nanometers. Remember, the longer wavelengths in the visible spectrum correspond to the red color of light. So now we have 3 times 10 to the 8 divided by 700 times 10 to the minus 9, 4.29 times 10 to the 14. And that'll be per seconds or hertz. And that's the red end of the spectrum. So there's the range of frequencies within the visible spectrum of light. The next question says, a little bit more complicated sounding, the first ionization energy for a ground state helium atom is 2370 kilojoules per mole. Calculate the maximum wavelength of electromagnetic EM radiation that could ionize the helium atom. What frequency is this? Ionization energy, remember the first ionization energy is the energy needed to remove the valence electron from the ground state gaseous atom. So for helium, 2370 kilojoules of energy would be needed to ionize 1 mole of helium atoms. Well, the first thing I'm going to do is convert that from per mole to just per atom. How much energy is needed per atom? So let's take 2370 kilojoules are required for 1 mole of helium. Let's get rid of the moles and replace it with just atoms. Using Avogadro's number, 1 mole is 6.022 times 10 to the 23 atoms. So grabbing a calculator, 2370 divided by Avogadro, we get 3.94 times 10 to the minus 21 kilojoules. Now I should have probably also converted that from kilojoules to joules, but I guess I'll just do that with one more unit multiplier here. So I'll just add on one more, get rid of kilojoules, switch to joules. There's 1 kilojoule has 1,000 joules. So we get 3.94 times 10 to the minus 18 joules per atom. There we go. So we've got the ionization energy now for just 1 atom, and we've expressed it in joules instead of kilojoules. So now that we're here, we can ask ourselves, well, what wavelength of light would correspond to that energy? If we think of Planck's equation, we know that E equals hc divided by lambda. Lambda is wavelength. So if we rearrange this, multiply both sides by lambda, and then divide both sides by E, we get lambda equals hc divided by E. So using Planck's equation, 6.626 times 10 to the minus 34 joule seconds, Planck's constant, 3.00 times 10 to the 8 meters per second, speed of light, divided by this energy required for 1 atom, 3.94 times 10 to the minus 18 joules, and we're going to get joules canceling, seconds canceling. We're going to get meters as an answer, which is the wavelength we're trying to find. So let's do that. So 6.626 times 10 to the minus 34 multiplied by 3 times 10 to the 8 and divided by 3.94 times 10 to the minus 18. We get 5.05 times 10 to the minus 8 meters as the wavelength. Now, why did it say maximum wavelength? Remember that energy and wavelength are inversely related. So this wavelength gives us the exact amount of energy we need, but any wavelength shorter than this would have more energy than we needed. So they would also be able to ionize the atom. So this wavelength is the shortest one, the longest one that would work. Any wavelength shorter than this would also work because it would have more energy than needed. Now the question was also, what frequency of light is this? So I'll take the equation C equals lambda nu and I'll rearrange it. Nu equals C divided by lambda equals 3.00 times 10 to the 8 meters per second divided by 5.05 times 10 to the minus 8 meters, and I'm going to get per seconds as my answer. 3 times 10 to the 8 divided by 5.05 times 10 to the minus 8, and our frequency is rather large, 5.94 times 10 to the 15, which makes sense. We remember when wavelengths are short, frequencies are large. Frequencies are usually going to be big numbers like that. All right, so there's two other questions involving light and basic calculations with light. Let's switch over now to look at the Bohr model of the atom. This is the other major calculation in this first unit of grade 12 chemistry. Niels Bohr is famous for the Bohr model of the atom, which has been replaced. He helped replace it with the quantum model of the atom, the quantum mechanical model of the atom, which views electrons now not just as particles, but as particle waves. In his original model, though, Bohr calculated the energy of electrons in different orbits within the atom. He gave us this equation. This is a simplified version of his equation. In a physics class, you'd look at this in more detail. He calculated the energy of the electron in the nth energy level. So where n is the energy level. I'll do it over here, I guess. This is the energy level, or the orbit, if you prefer. And we know that its values go from 1 to 2 to 3, etc., up to infinity. So n is any natural number, basically. Z, in his equation, is the atomic number of the element that you're talking about. So for hydrogen, periodic table, Z is equal to 1. Now, Bohr's equation had a couple of big limitations, but the biggest is that it really only works if the atom you're looking at has one electron. So for a neutral atom, it works only for hydrogen. It will also work for cations that have one electron, so helium plus 1. Helium normally has 2 electrons, but helium plus 1 has 1 electron. Lithium 2 positive would also work with this equation. So the atomic number is usually going to be a 1, because we're usually going to talk about hydrogen, but it can also refer to a helium cation or a lithium cation, in which case Z would be a 2, a 3, etc. So let's jump in and use the equation. Calculate the wavelength of light emitted when an electron falls from the 6th to the 3rd energy level within the helium cation He positive. So helium has only 1 electron, so we can use Bohr's equation. Its electron starts off in an excited state up in the 6th energy level, and it's going to fall back down to the 3rd energy level, which will still be an excited state. In falling from a higher level to a lower level, energy is going to be emitted. And so that energy is going to come out in the form of electromagnetic radiation, and we're going to calculate the wavelength of that radiation. There's 3 steps to doing this problem. Step 1, we're going to calculate the energy for each energy level. What was the energy of the electron in the 6th level? What was the energy in the 3rd level? And we're going to use Bohr's equation to do that. Then in step 2, we're going to find the difference in energy. So if it falls from level 6 to level 3, how much energy does it lose? And finally, we'll use Planck's energy equation to say, well, if it lost this much energy, what wavelength of light would that correspond to? So the first thing we'll do is use Bohr's energy equation to find E6 and E3. So E6, the energy of the 6th energy level, negative 2.18 times 10 to the minus 18 times, now Z for helium, the 2nd element on the periodic table, is a 2, so 2 squared, over n squared, so over 6 squared. Okay, so there's the energy level 6. Doing the same thing for level 3, negative 2.18 times 10 to the minus 18 times 2 squared, still helium, over 3 squared. Okay, a very common silly mistake I see on tests and on exams is that people mix up the atomic number and the energy level. They put them in the wrong order. So grabbing a calculator, we get negative 2.18 times 10 to the minus 18 times 2 squared is 4, divided by 6 squared, which is 36. I get negative 2.42 times 10 to the minus 19 joules is the energy in level 6. Doing the same thing for level 3. Now, if you want to save some time on a graphing calculator, you can go second function, enter, to bring up the last thing you did, and then I'll just, instead of typing all that in again, I'll just divide now by 9. So, negative 9.69 times 10 to the minus 19 joules. So now, the second thing we want to do is calculate the energy that's released. In fact, we're going to calculate the absolute value of the change in energy when the electron goes from level 6 to level 3. Absolute value, remember, makes an answer positive. So what we'll do is we'll take the absolute value of the final energy level, E3, minus the starting level, E6. So using the numbers above, the absolute value of negative 9.69 times 10 to the minus 19, take away negative 2.42 times 10 to the minus 19. Okay? This is, for some reason, a place where a lot of people make mistakes just typing in these numbers on their calculators. So negative 9.69 times 10 to the minus 19, take away negative 2.42 times 10 to the minus 19. Just do it carefully and you won't go wrong. Notice the answer comes out as negative, and that's because energy is being lost. The electron's falling from a higher level to a lower level, so it's losing energy. That's why it's negative 7.27, but we're going to make that positive because we're taking the absolute value. So 7.27 times 10 to the minus 19 joules. There will be the answer for the energy lost, or the energy emitted. Okay? The third thing we're going to do now is calculate the wavelength. What is the wavelength of this light? It comes out with this much energy. What's its wavelength? Well, Planck's equation says E equals hc divided by lambda. So now if you rearrange Planck's equation, you get lambda equals hc divided by E. So 6.626 times 10 to the minus 34 joule seconds, Planck's constant, 3.00 times 10 to the 8 meters per second, speed of light, and then divide that by the energy loss, which was 7.27 times 10 to the minus 19 joules. And that's going to give us a wavelength of 6.626 times 10 to the minus 34 times 3 times 10 to the 8, and divide by 7.27 times 10 to the minus 19, we get 2.73 times 10 to the minus 7 meters. Now, it didn't ask us to do this, but if we were to convert that to nanometers, what would that be? Well, let's just do a quick unit multiplier. 2.73 times 10 to the minus 7 meter. Get rid of the meter, switch to nanometer. 1 nanometer is 1 times 10 to the minus 9 meters. And that's going to be 273 nanometers. So that's the wavelength of light that would be emitted during this electron transition. All right. You do the last question yourself. It's similar to what we just did. Pause the video and see if you can solve this one. We want both the wavelength and frequency when an electron falls from a third to second level in a hydrogen atom. So 3 steps. I'm going to start by finding the starting and the final level energy levels. Negative 2.18 times 10 to the minus 18 times z squared, in this case, will be 1 squared. Hydrogen's atomic number is a 1, divided by 3 squared. and negative 2.18 times 10 to the minus 18 times 1 squared over 2 squared. So grabbing a calculator again, negative 2.18 times 10 to the minus 18 divided by 9, I get negative 2.42 times 10 to the minus 19 joules. That's the energy the electron starts with. And doing the calculation again, but this time dividing by 4, we get negative 5.45 times 10 to the minus 19 joules. And that's the energy it finishes with in the second energy level. Next, we'll find the change in energy as we go from level 3 down to level 2. And we'll take the absolute value of that. So the absolute value of the final level minus the starting level, the absolute value of negative 5.45 times 10 to the minus 19 minus negative 2.42 times 10 to the minus 19, and we're going to be very careful as we type that in our calculators. So equals negative 5.45 times 10 to the minus 19, take away negative 2.42 times 10 to the minus 19 equals, and again the answer comes out in the calculator negative because energy is being lost. We're going to make it positive because we're taking an absolute value. So 3.03 times 10 to the minus 19 joules. And that's the energy emitted or lost. Third thing we'll do is we'll use Planck's equation to find the wavelength. I apologize for the shadows here. The sun is coming in now rather strongly. So we get Planck's equation equals hc over lambda. So therefore rearranging, lambda equals hc over E. So plugging in our constants, 6.626 times 10 to the minus 34 joule seconds, 3.00 times 10 to the 8 meters per second, and divide that by the energy, 3.03 times 10 to the minus 19 joules, and we get a wavelength of 6 times 10 to the minus 34 times 3 times 10 to the 8, divide by 3.03 times 10 to the minus 19, 6.56 times 10 to the minus 7 meters, which, if you prefer, is 656 nanometers. And then the frequency, we'll just rearrange c over lambda equals 3.00 times 10 to the 8 meters per second divided by the wavelength, 6.56 times 10 to the minus 7 meters, and we get 4.57 times 10 to the 14 per seconds as our frequency. So there are pretty much all the major calculations that we would have to do in this first unit of grade 12 chemistry. Equations involving light and wavelengths, frequency, and energy, and then problems involving Bohr's energy equation, electron transitions within the atom.